Hello, SREcon. My name is Jeremy Blosser. It's 10:55, so we're going to get started. I am the Principal Operations Engineer at SparkPost, and I am here to talk to you about a major incident we had about a year ago, May 2017, which we lovingly call internally the day the DNS died. And then the slides are posted online already at tinyurl.com/spdnstalk because I use tinyurl because I'm old school. We'll operate slides. All right, real briefly introduction here. SparkPost, some of you may know us as Message Systems. We are a high volume transactional email software and services vendor. We send a lot of email, trillions of messages a year. We estimate that over 30% of the world's non-spam email is sent using our software. We do about 15 billion messages a month through our cloud offering, which is the topic today. A lot of mail means a lot of DNS. As Brent Chapman says, DNS is the original microservice, and we really know the truth of that where we are. We do 8,000 queries a second in our environment. That's about 20 megabits sustained traffic, and that's just the queries. That's not even the responses. We push enough DNS that our support teams have for vendors have at times suggested we must have been rooted because nobody could push that much DNS, but we do. And of course, we have to resolve along multiple resolution paths. With email, we're more dependent on DNS than we are almost anything else. But DNS is easy, right? We all know this. No comment. So brief outline introduction we're going to talk about our previous DNS designs as we moved into the cloud and kind of how we ended up where we were the day of the event. We're going to walk through the event in a fair amount of detail. We're going to look at what we had to do after the event to put a new DNS solution in place to make sure it doesn't happen again, lessons learned along the way, and we'll get to some Q&A. So previous DNS designs. In the beginning was the MTA, and it was good, right? Our cloud story is pretty much like most other companies. We've been doing on-premise software for 15 years. Eventually wanted to deploy that in the cloud for others to use that were, smaller customers, et cetera. So our early implementation was just put the thing in the cloud, build a resolver cluster, and let it point at the upstream DNS. Amazon does offer a DNS service, and we'll talk about that, but we were new to AWS, and we weren't really sure if it could handle our load because we have a lot of it, so we went ahead and stuck with what we knew. Of course, we needed more than public resolution sources. We also had to resolve private names. We had to resolve AWS endpoints, which are in the public DNS, but we went ahead and wanted to go to them shorter path internally, going against Route 53. And because we're a mail provider, we also have a lot of, DNS gets overloaded in mail a lot, and we needed to resolve the RBL, the real-time blacklist for IPs and URLs in our messages so that we make sure we're doing due diligence to do our job to not let our customers spam people. Our compliance tier actually is the single highest consumer of DNS in our environment. We have nodes there that do a kilo query a second by themselves. And of course, our clients internally were more than just the MTAs, the app tier, the DB tier, and our administrative tier all had to go against DNS. So this is a pretty basic sort of infrastructure. Obviously, it's a cluster, it's a beefy cluster. Basic design, not necessarily flexible, but not necessarily wrong either. Nothing can go wrong with this, of course. Famous last words. So the first thing we ran into early days was that network infrastructure-wise, again, going into AWS, and their network model is a little different than a traditional model. We had put the resolver cluster in a subnet with the client nodes that were going to talk to it behind the NAT infrastructure. And we hit a problem pretty early on when the NAT couldn't keep up with that, so that worked until it didn't, and then we moved it out in front of the NAT. We iterated to get past it, and then we kept going, and that worked until it didn't. And one day we hit some unknown limits where the MTA tier wasn't getting responses back as fast as we needed it to. Again, early days with AWS, we didn't have our support relationship fully established yet, so we didn't really have a lot of feedback from them. To find out what it was. We later learned that it was probably something like an automated DDoS protection net caught us up because we're sending thousands of DNS queries a second. We look like we're participating in a DDoS. That's probably what caught us. But whatever, we iterated, we moved past it. We moved past it by going ahead and going with AWS's solution. For those that maybe don't use AWS, most cloud providers have this though. They have, the standard virtual private cloud system, your private networks that you can build, and they all have their own CIDR ranges. And they have, standard broadcast and network addresses on either end. They also have a reserved .2 address in each CIDR that is, if you hit it, it will be a Route 53 backed DNS resolver that can resolve anything on the public internet and any private zones that are defined inside of Route 53 that VPC is allowed to talk to. And it's very high performance, and they said, it should be able to handle anything. So we went ahead and repointed just our MTA queries to go through the AWS VPC tier. Surely it can keep up. It's just DNS. And that worked until it didn't. It didn't when we hit an undocumented at the time, because Amazon didn't really think people would run into it, limit where you can throw 1,024 query packets per second per network interface against an AWS VPC resolver, after which point it assumes you're trying to do something nefarious and imposes a back-off throttle. So our traffic slowed to molasses, and it was a bad day. Didn't have a full outage this day, but we definitely had degraded service. So never mind Amazon's VPC service, we went back to what we had been doing, better relationship with them at the time, so we were able to explain our service model. They were coming to understand us better, that we really do push that much outgoing traffic, including DNS, and they were able to put things in place to prevent us from hitting the automated DDoS protection, etc. Use your own resolver cluster was the recommendation. It'll be just fine. And it worked until it didn't. And one day we outgrew yet another undocumented limit. And this isn't really one that Amazon even fully understands internally. It's more of just you've got your advertised performance of a given node in a normal sort of service model, which an Amazon normal service model is like streaming media or something, or pulling content. You contact them with an HTTP request, they give you something back, your app tier, etc. Not someone injects a message, processes it through a template on the back end, and injects it to 4 billion people or something, which is what we do. Right, so atypical service model, atypical traffic. This is the time we were on the phone with support, and they said this node is this cluster is pushing 40 megabits a second. You say that's DNS. You're cracked. Call us back when you've patched your systems and are fixed. I went, no, don't hang up the phone. We're not cracked. This is legit traffic. And then they said, well, if it's legit, then you can't push it on that level of infrastructure. It was kind of a trust the support guy who's giving you the intuitive information from his experience thing. So we went ahead and, they said make the instances bigger. So we made the instances bigger. Again, iterating, fix the problem. But, at this point, we're iterating, we're adding capacity. We're starting to reach kind of, fundamental design limits here. We're playing whack-a-mole. And we started thinking through a major refactor to prevent, because this one was an outage, and it was at the time the worst outage we'd experienced. If only we knew at the time what was on the horizon. But it was a few hours of really degraded service, unhappy customers. So we didn't want that to happen again. So we started to talk through a redesign, and didn't quite get there before May of 2017. So it was a day like any other day in SRE land. Dev had been running some performance testing and pre-prod in the morning, so we had some alerts firing here and there as there was some spillover, nothing to be really concerned about, but meant that when the on-call engineer started to see some noise, he thought maybe it was just internet weather. We had alerts firing and clearing all day long. These were DNS alerts, so we're kind of sensitive about that. So, one of the other engineers starts looking in and has a comment here that this might be something new and exciting. And then on-call engineer realizes that from his workstation even, we can't get query responses back from the core DNS infrastructure. And the other engineer expresses some concern at this. And then my favorite thing to see in a Slack channel ever is Page Jer. I'm Jer, if you don't know. I was the DNS SME. So, and if you attended Brent's workshop yesterday on incident response, this was the detect alert phase of incident response. Try to tie some of that into here. So what did our metrics look like? Well, the problem was DNS. Our metrics are DNS dependent. So our metrics looked fun and exciting. And if you could, we have normal traffic. This is the DNS cluster's aggregate CPU, which was one of the things we were watching on the DNS cluster already at the time. It spikes and then it kind of goes to scatterplot land because the metrics cluster can't find the nodes anymore to get data, and vice versa. It's even more dramatic when you go to our MTA. One of our MTA clusters, aggregated CPU, you see It's trucking along. We start to see some spikes, and then we have dead air, and then we have a bit of a blip. And then as the day progresses and we start to remediate, we finally manage to turn the lights on here, and kind of wish we hadn't, because they were busy. And then, one of the worst things for us to see, this is one of our major customers sending outgoing mail. Bursty mail is very bursty, but we definitely don't want to see it trending towards zero, as was the case here, and it was not a good time. Sorry if any of you didn't get your bank account statements that day. For a while, delayed. We got them to you. So it was near total impact. Sending mail was definitely impacted. For the most part, our customer mail injection was not impacted, and this is the core 9 that we track. Mail is bursty, mail can be delayed in sending, but we always want to make sure we take it as soon as the customer gives it to us, even if we're a little late in getting it back on the wire. So for the most part, we held that one on here. There were some of the customer mail clusters that just got so overloaded they fell over and they wouldn't even come back online until it was fixed. They went to their happy place. App and DB traffic was impacted because, again, back to that diagram, they're all talking through the same cluster. So this is a huge problem when it was down. Mail was impacted, app and DB are impacted. Metrics is impacted, as I showed you. Not monitoring. Our monitoring is DNS isolated, so we knew everything was broken. Our on-call may have wished the monitoring was broken, but admin logins were affected. This was one of the worst things. Not just our SSH connections, but even our VPN connectivity, because our VPN uses multi-factor auth, which has a multi-factor auth API vendor endpoint DNS dependency, or it did, doesn't have it anymore. It's isolated now. But, it was kind of just one of those days when, one thing goes wrong and then other things go wrong and then everything just goes wrong. And this is kind of how it felt. So now we're into the respond phase of incident response, but we're kind of diagnosing blind because so much of our tools that we relied on aren't functioning because they have DNS dependencies. We also had kind of a fundamental lack of insight into our DNS. As a support service, we were monitoring CPU and memory utilization across the cluster, but we weren't instrumenting it heavily internally. I don't know if that would have helped us much, but it might have helped us point to root cause a little bit quicker. But regardless, we're unable to reach our support system, so we couldn't even connect to things to diagnose. So we're diagnosing blind from 2 directions. We can't see things, and what we can see isn't that useful. We went back to what we'd seen before. Is it Amazon throttling us again? Is it a capacity limit we don't know about again? So we went ahead and tried, now we're, into the mitigation phase. We tried the things that worked before. We centrally forwarded some of the traffic to the central VPC Amazon resolvers, which immediately stopped responding, which was kind of expected. We knew we were pushing way more than 1,000 queries per second across those interfaces. And we tried increasing capacity. We went to like 10x capacity. Hooray, the cloud, we could do this quickly. But oddly enough, those new 10x capacity servers within 2 seconds had the exact same symptoms, which was very strange. Never had seen that one before on this tier. So what we had to do was go ahead and move to not a central repoint to the VPC resolvers, but since it's a resolver per VPC and per network interface, and we have multiple VPCs inside the environment and multiple network interfaces, certainly we had some wiggle room, but we had to go do it per node. So we had to go edit resolve conf on every single node, and I'm going to come to that in a second. But let's talk about resolve conf for a moment, because it has a lot of issues that we weren't necessarily aware of. I don't know how many people are. Resolve conf is limited to 3 entries for the name server. So you can add 5, 6, 10, it doesn't matter. Pretty much everything that uses resolve conf, and you can configure it, but you have to configure everything. Bottom line is it's all going to use just 3, the first 3 you list. And they're always tried top to bottom. So you may put in 3 and hope for some round robin or hope for some load balancing. It doesn't happen. It starts at .1 if that's the first one in there. Every query goes there. It doesn't go to the second entry unless the first one times out and fails. And that may not even happen is the other thing. The practical retries are very limited. Most things that have a resolver library, whether they're using the glibc one or they're using their own, they read resolve conf, they use the first entry. If it fails, they'll try the second one. If that fails, they'll try again by starting over, by tossing away whatever call they're doing a new call starting at the top. So you may never even hit the third one, although in our experience, you're not completely down as long as at least the third one's there, but it's really choppy response. The biggest problem is that almost everything in the world I now know reads resolve-conf on startup and never again. So I don't just mean our software. I mean Nginx's resolver library does this. It reads resolve-conf. If you have to change it, mid-event or whatever, push it out through your config management system, great. Nginx don't care. It's going to keep using what it used at the beginning, so you have to restart the world per instance to get these changes to be picked up. And our resolve-conf at the time was pushed by CM, but it was global. It was the same 3 entries, and we were not well positioned to be agile to respond to this. So we did it the long way around. We edited resolve-conf largely manually because our config management was even impacted. Some of it, we were kind of between systems, and the old system was DNS isolated. The new one wasn't. So we had to do it per instance, mostly manually with login timeouts. I think one person said it took them 4 hours to get onto one machine because our LDAP was supposed to be DNS isolated, but it wasn't. We learned that the hard way. It did provide breathing room. Eventually, the main resolver cluster recovered as the load was removed. The app tier actually was able to recover. It was one of the first things we moved, was able to recover within a couple hours. Major customers had mail moving again within 4 or 5 hours. The time from start to full finish was 7 hours. It was not a great day. We were in a dedicated Slack channels, tracking things on Google spreadsheets and stuff because it's what responded at the time. This is a better picture. This is app tier recovering within those first couple hours. This is an SQS queue showing our webhooks, which are DNS dependent. So that's the backup on the queue increasing linearly until they get to talk to different DNS, and then they start coming back down. Hooray. So what the heck was going on here? During the event and after, of course, we started trying to figure out what was going on with the limited visibility we had, and as visibility improved, as we got some remediation going, what we were seeing consistently was asymmetric DNS packet flow, by which I mean we were sending queries out and nothing was coming back, and it wasn't, it's UDP. We're not going to get TCP resets, but it was like we were just throwing them off the edge of the world, off the edge of the disk, and nothing's ever there. TCP dump, AWS network flow logs, just raw/proc information was all telling us basically the same thing. We're talking and no one's listening. And if you can see the TCP dump, one of the tools we wrote on the fly there to do an in and out, we were seeing roughly 300 responses for every 5,000 queries we sent, which is about a 94% failure rate. But why, right? What the heck is going on here? We were able within the 48 hours after the incident to recreate it with AWS in a dedicated test environment. And pretty quickly, they actually noted that day what the issue was. Any bets? Connection tracking, as in stateful firewalls, as in undocumented connection tracking, as in how many undocumented limits does AWS have, people? Once we got all the right eyes on it in the room, they were really quick to figure out what it was and tell us what's going on. Again, it's a documented limit. It's an undocumented limit at the time that they don't talk about. So a little bit about stateful and stateless firewalls. So if you're using normal traffic like SMTP, TCP traffic, right? You have your firewall allows traffic out to port 25 in the world, and you talk to a server and you talk to its port 25 from some random hide port on your side, and it talks back to said random hide port from its 25, and your firewall doesn't allow incoming stuff from random hide port numbers, but your firewall noted on the way out that there was a random hide port to 25 connection made, and it's watching for the response. That's a stateful firewall. It requires memory in kernel for the firewall device to track, though, and the more connections that you have, the more resources you're using. This compared to stateless firewalls, where you send a connection out on UDP DNS port 53, and you're just expecting all kinds of people in the world to respond back from their own 53 to your high ports, and you don't bother tracking them, you just let them in. And normally in the world, TCP protocols are stateful, and you use a stateful firewall, and UDP is not necessarily, so you don't. But Amazon security groups, we now know, are all stateful. So if you're using a security group and you're applying any kind of firewall rules there, you are invoking a stateful firewall. The limits are really, really high, but 640K isn't always enough for everybody. And they're applied at the security group level. So when we were expanding the cluster 10x and putting it all in the same network infrastructure, same security group models, that's why within 3 seconds we saw the exact same problem. So after action, we sat down and looked at it. Our incident response process was actually functional, except that our ability to actually have visibility and respond was incredibly compromised. The data we had, we did good things, we just didn't have great data. And we were, of course, at this point, absolutely seeing the limits of iterating across this infrastructure, and it is time to do a new design. So what does the new design look like? This is kind of wall of text, but hopefully I'm speaking about this well enough that all of these make sense to you at this point. We needed to resolve all our needed name sources. We needed to be able to modify how infrastructure worked for DNS without changing resolve conf anywhere. We needed to be able to avoid any Amazon throttling and connection tracking that they documented to us. We needed it to be multi-cluster and isolate components from each other so MTA didn't use the same DNS that authentication did. We needed to distribute it across multiple resolver clusters for the same reason. We wanted to minimize latency. We hadn't worried about this a whole lot because DNS is cheap, but with the number of queries we're pushing, we started to get really, really specific about shortest path inside of the cloud environment and what we knew about the infrastructure between the data centers there. We wanted to add more effective caching. Our MTA product caches opportunistically DNS query responses, and Unbound, of course, does as well. But we wanted to get more local caching involved at the individual instance level. We wanted to do caching while respecting TTLs on DNS responses. This is kind of one of the things that had kept us from going to local caches before, because the cloud is pushing TTLs and DNS down towards zero. Many of you have probably seen our own SMTP endpoints are Amazon ELBs, which implement load balancing through DNS, so they're all 60-second TTLs. So we want to be able to cache DNS responses to be able to push mail. If you guys publish an update to your MX record, we want to respect it immediately, but we also need to be able to deliver mail. And if you haven't actually changed it in 4 months, we can keep using it. We want to keep using it. And we wanted to increase our DNS profiling and monitoring. Again, I'm not really sure how much that would have helped us, but every little bit, right? So this is what we ended up with, and it's complicated now. We're going to walk through it a little bit. As we talk through it, the main three things here are that we have a dedicated MTA resolver cluster at the top there. It's separate from the one at the bottom that the other tiers are using. And this is just an example. We also can separate out other tiers like compliance. It's actually in its own network segment with the dotted lines there, so it's in its own VPC so that we can apply Amazon's solution for the security group problem while still maintaining security. It's routing separately to the AWS VPC Resolver and our Unbound Resolver cluster, depending on the kind of traffic it's after, and it's making that decision at the local cache level, and we're actually running local caches everywhere, and we're running 2 local caches everywhere, which is a little weird. It's about that shortest path piece, and we'll talk through that in a minute. So the network configuration you saw there, we have dedicated VPCs for isolation, like I said, and then Amazon's solution for the security group issue is Amazon has 2 firewall models in place in its services. Security groups are stateful. Network ACLs that you apply at the higher level are stateless. So they said, put the cluster in its own VPC, add security groups that are */ allows, everything goes through. That will cause it to never invoke stateful firewall tables. And then at the network ACL level, add allows, and we did for everything going out to 53 is allowed, and then everything coming in from a defined range of ports that our Unbound tier uses for its outgoing ports is allowed. And you won't hit any limits from stateful firewalling. Hooray. We also went to multiple network interfaces and multiple IPs per interface on the resolver cluster. This has helped us, kind of hopefully dodge any more hidden, undocumented per network interface limits that are out there. But it also helps with that resolve conf issue, because I can take one cluster, put 20 IPs on it, throw those IPs into the CM random pool to distribute across instances, and if that resolver has issues, I can redistribute the IPs without necessarily having to tell anybody in the world that the resolver changed, which has actually been a thing we've had to do, and it's been really useful. Sorry. And then we have query traffic favoring the same availability zone, and we'll talk through that when we get to the Unbound piece, or the DNS mask piece. So our resolver configuration for Unbound, it's been heavily tuned now. We hadn't really gotten into that originally, but we absolutely have now. We're about 40x performance out of an individual Unbound node at this point, which is just what we needed, right? The ability to push more DNS to Amazon. That's great. But no. Mentioned the multiple interfaces, multiple IPs. We've also, Unbound actually has a feature that's new in the last year or so. If you need to do heavy DNS like this, called serve expired. What serve expired does is respect the TTL. So when the TTL expires, go ahead and make a new request. But if you don't get a response back or you get an error back, keep using the last good value until you get a good value back, which is kind of a magic button for us in the scenario we're in. Haven't hit an event yet to actually see how well it works. We've tested it, of course, but we're hoping it buys us some time if we hit something like that. And we went ahead and built the thing bigger, so it's about 5 times the size it used to be now, just in case. So at the OS level, and this is where it gets to be a little magical, we're running DNS mask for the local cache, and the URL's at the end of this. It's a lightweight, pretty high performance local caching resolver. Most of you are familiar with. You're running it on your desktop probably. We're running actually 2 instances of the service. They listen on 127.0.0.1 and 127.0.0.2. What's different about them is which upstream resolvers they point to. So Amazon, like any cloud provider, right, has multiple, they call them availability zones, multiple data centers that are all different from each other. And for the most part, our clusters are for DR and for fault tolerance, we just deploy across availability zones because it's pretty low latency, even if they're on multiple parts of a campus. But for DNS's sake, we have the 127.0.0.1 resolver pointing to all of the DNS upstream resolvers that are in the same availability zone. So you don't go outside that data center for your response. And then the .2 resolver DNS mask instance points to all the ones that are outside that availability zone. So that's the failover model. So we're staying shortest path inside the same data center unless we have to get out of it. We've configured DNS mask as much as you can. It's very, very lightweight. We've cranked the concurrency for requests at the same time through the roof. And then the max cache size it ships with is like 150 entries, which is comical to us. So we patched it to be, I don't know, it's like 2 to the 10th or something now. It's pretty big. And then Etsy resolve conf on each instance points to those 3 entries that you get, 127.0.0.1, 127.0.0.2. And then since we get a third one, we go ahead and point to an upstream Unbound resolver in the same availability zone, which is useful if DNS mask has catastrophic failures, which actually has happened once. We had an automated upgrade that broke it, locked localhost 53 on every instance, and stuff slowed down, but it was still able to get to that third instance, and we stayed afloat. So again, one more look at the graph. It works. It works really well. We've actually had several events happen in the last year, DNS related, that could have become the shells all falling over again, but they didn't because we had room to breathe. We were able to get in and diagnose things as soon as they started and move everything around as we needed to. I'm not going to walk through those because of time, but bottom line is we're much happier with this setup. So what did we learn along the way? We learned that AWS's main service model is pull, not push. Touched on that briefly earlier. Related to the above, not all your cloud provider limits are going to be apparent, especially if your service model is atypical for them. Make sure they understand your business. We're actually very happy right now with AWS, but there's been a learning curve on both sides for them understanding our business and us understanding where their limits are and what we need to do about them. Instrument your support services, protect them from each other. Validate your component isolation. Like I said, our LDAP was supposed to be isolated from DNS and it wasn't. Our VPN, we hadn't even thought of that one because it was such a minor thing. But if you think you're isolated, test it, game day this, however you need to. This is, a great opportunity for chaos. Resolve conf is not agile. It's not even eventually consistent. Touched on that one. Iteration won't solve it all. Sometimes you have to tear it down and start all over again. And of course, the last thing we were reminded of is that it's always a DNS problem, except for when it's a firewall problem. Here's some references. You can pull up the talk. This is AWS. So I mentioned that those limits were unpublished. Amazon's worked with us, and they are now published. This Amazon white paper talks about advanced DNS solutions and talks about the details I mentioned today. They've actually since also added the connection tracking info into their security group docs that are linked there, linked to Unbound, Amazon's VPC Resolver, and DNS Mask software that we're using. Yeah. Any questions? Please come to the mics because I'm half deaf and I won't hear you if you don't.
I'm James Hall from Bloomberg. DNS is one of those core services that everybody kind of uses and just assumes it'll be there and always kind of work. What are some of these other core services that everybody just kind of depends on and could bite? Maybe not DNS, but anything else that you can think of.
Auth, LDAP and VPN, NTP, absolutely, and monitoring and metric stuff. You want to make sure they're isolated because you need them to spot an outage. But auth, NTP, and DNS are the things that get that paged error in the Slack channel more often than anything else in our environment, I think. Other questions? I think somebody's coming. Yeah.
Yeah, so you mentioned that you were using LDAP in production for authentication. Have you thought about removing that so you don't have a network dependency in this kind of like total outage?
Sure. So we actually, we do. We have LDAP for normal user management, right? We have the normal kinds of safety nets for our administrative users if we need to bypass LDAP. The weird thing was none of that was working. There should not have been a DNS dependency on our override local user account, super user accounts getting in, but it was there. We've debugged that since and resolved it, and it's no longer there. But thanks for clarifying that.
Very quick question. Was DNS load balancing a option?
Sorry?
Was the option of using a load balancer to load balance DNS?
So, sort of, that's just that to us that adds another tier for potential failure. Amazon's load balancer models don't really support UDP that well natively. The newer network load balancer they're making does, but it still has some issues. So yeah, it's such a low-level service that load balancing it versus having a large cluster and distributing, it by configuration management has been the more reliable option for us. Yeah.
So I had a question about certificates and DNS because they tend to be highly interlinked also. So are you self-signing certificates? Does that play into your DNS rollout? How are you handling the interaction between your certificate infrastructure and DNS?
How are we handling the relationship between certificate infrastructure and DNS?
Yes.
That's a good question. We use various third-party upstream for external certificate stuff, which for us with SMTP, opportunistic TLS is the main place we run into it, and our API tiers, etc. I think that's an area where our big DNS dependency is more push-related than it is people making requests from us. It's like our app tier wasn't down from a front-end perspective at all, but it was unresponsive because it couldn't talk to the database because it couldn't find the database, which was using load balancing, but it's using DNS to find the load balancer, etc. I think, for the most part, we're pretty isolated there. We don't have a lot of dependencies, but I'm probably going to take a note to check on that so we're not assuming things.
If you're self-signing the internal certs, then the naming of the servers, if you're injecting the name into those servers, it could cause additional. That was just why I was.
Yeah, they're pretty discrete services. Like all of this stuff is our SRE team manages, and our internal certificate PKI is our IT team. So they're completely different systems, for sure. But we should check into potentials there.
Thank you.
Yeah. Other questions? Okay, thanks.